Welcome to today's webinar, Introducing VPC Support for AWS Lambda. Our presenter today is Vyom Nagrani. Vyom is a Senior Product Manager for AWS Lambda. He holds an MBA from the University of Michigan and has previous experience across product management, product marketing, and product engineering. Today with us, we also have Ajay Nair. Ajay is the Senior Product Marketing Manager for AWS Lambda. Correction, it's the Product Manager, as it shows on the spec. Ajay will engage with you and answer your questions throughout today's presentation while Vyom presents. Vyom, welcome, and I'll pass the floor to you.
Okay, thanks, Bowen. Hello, everyone, and welcome to Introducing VPC Support for AWS Lambda webinar. My name is Vyom Nagrani, and I'll be a presenter for today. I also have here with me Ajay, who will help address your questions over chat throughout the webinar. We will also do an open Q&A at the end of the webinar if time permits, where I will address the commonly asked questions. A quick note on the Q&A, we welcome all types of questions during this webinar, but the Q&A panel unfortunately will not be able to address roadmap questions or timelines of upcoming features on these services. So we do apologize for that in advance. The intention here is to help you understand how you can connect your Lambda functions to VPC in depth. So we have to give priority to addressing your technical questions related to Lambda and VPC. We also may not be able to address specific debugging questions or troubleshooting questions for your setup. If you have any questions on those lines, then please do direct those to the AWS Lambda forums, and we'd be happy to look at them for you offline. With that said, let's jump into the webinar. We will be segmenting this webinar into 3 parts today. First, I'll start off by a brief overview of AWS Lambda and Amazon VPC for those of you who are new to either of these services. Next, we'll walk through an in-depth demo on how to set up a Lambda function to access resources within a private VPC. Lastly, we will go through the best practices on configuring Lambda to be able to connect to your VPC. So let's start with a quick introduction about AWS Lambda. AWS Lambda lets you run your code without provisioning or managing servers. You pay only for the compute time that you consume, and there is no charge when your code is not running. With Lambda, you can run code for virtually any type of application or backend service, all with zero administration. No, just upload your code and Lambda takes care of everything required to run and scale your code with high availability. You can set up your code automatically to trigger off of other AWS services, or you can call it directly from any web or mobile app. And Lambda makes it easy to execute code in response to events, such as changes in Amazon S3 buckets, updates to an Amazon DynamoDB table, or custom events generated by your application or devices. With Lambda, you do not have to provision your own instances, and Lambda performs all the operational and administrative activities of the underlying infrastructure on your behalf, including capacity provisioning, monitoring fleet health, applying security patches to the underlying compute resources, deploying your code, running a web service front end, monitoring and logging of your code in your execution. Lambda provides easy scaling and high availability to your code without any additional effort on your part. You can invoke a Lambda function using a custom event through the AWS Lambda's invoke API as well. This makes Lambda a good platform to build data-driven auditing, analysis, or notification-based systems. And you can allow you to build these back-end services that perform well at any scale. So let's talk about the benefits of Lambda for building a serverless data processing engine. Lambda allows users to focus on building these powerful, dynamic, and modular applications in the cloud while not distracting your productivity in the undifferentiated heavy lifting of managing infrastructure. Lambda automatically runs your code on high availability compute infrastructure and, as I said, performs all the administration of the underlying compute resources. All you need to do is write the code. So the main benefit of Lambda when building these applications is that there is no servers to provision or manage. No, you don't need to plan for capacity. You no longer need to go through server patches or upgrades or software installation or worry about being paged when your servers are down. Also, Lambda runs your code only when needed with no unnecessary cost. With Lambda, you don't need to build out and maintain a fleet of servers and then pay for the time that they wait around sitting for their jobs to run. Instead, Lambda charges a low fee per request for the time that your code runs, making it cost effective to build solutions that scale from one request per month to thousands of requests per second with absolutely continuous scaling so that you don't have to see any performance difference at either end of the scale. The last benefit here is sub-second metering. AWS overall has changed the traditional IT behavior, where IT admins used to buy hardware servers and pay for everything upfront, and also get 3 to 5 year commitments on the hardware that they purchase, or even have up to 10-year commitments for data centers that you're building out. AWS changed this to allow customers to pay for infrastructure capacity in chunks of 1 hour, but AWS Lambda takes this to the next level, where you pay in increments of 100 milliseconds. This means that if your API call takes 15.7 seconds to execute, you pay only for those 15.7 seconds. So these three features put together allow you to get an effective 100% utilization on your compute fleet right out of the box. No more paying for idle, or no more being under provisioned for peak or over provisioned for the off season. Lambda manages this entire scaling and the infrastructure management on your behalf. From here, let's dive a little bit deeper into how AWS Lambda works. The few things I want to highlight is with Lambda, it's bring your own code. Lambda supports code written in Node.js, that's JavaScript, Python, and Java. And by Java, I mean any JVM based language, so it includes languages such as Scala, Clojure, etc. Our goal is to make Lambda a polyglot platform, that is a platform that supports many languages, so that there is no new language for you to learn for using AWS Lambda. You can include existing libraries, or you can even bring native libraries packaged into the same into a format that you can upload to Lambda, and Lambda will execute the whole package for you. The second is we have a simple resource model. The only knob you need to dial is memory to decide the size of your Lambda function. And you can select the memory in steps of 128 MB to 1.5 GB in increments of 64 MB. And we allocate CPU and network proportional to the amount of memory that you configure. The report at the end of the function gives an actual usage of this memory and that is being used by the function, so you can fine-tune this setting over time. We also have flexible invocation paths, so you can have both event or request response invoke options, which gives you the option of choosing between synchronous and asynchronous execution of your code. Also, you can integrate the invocation with various AWS services, which allows you to bundle these services together and quickly build applications that can both consume the data as well as process the data. We use very fine-grained permissions for AWS Lambda using the IAM roles for execution permissions, and you can use resource policies for AWS event sources to grant them or control permissions of which event source can invoke the Lambda function. When authoring functions, you have the AWS SDK built in. When you are building applications in Node or in Python. With Java, you can always package in the SDK as a dependency package. When you're building the functions, you can the system will handle inbound traffic, but outbound connections to an outside port is limited. However, you can use things like processes, threads, /temp files, sockets, etc. in the same way in which you are used to building code on any other box. For deployment options, you can author functions directly using the WYSIWYG editor we have on the Lambda console, or you can package your code inclusive of all dependencies and even binaries into a zip file and upload it directly to the Lambda console or to Amazon S3. We use CloudWatch for monitoring and logging. So we have a bunch of metrics that go to Amazon CloudWatch, including things like the request count, the number of errors, the net latency, and the amount of functions which were throttled. And all of the logs, inclusive of system logs and user logs, go to CloudWatch logs. The one thing to call out is that Lambda functions are stateless. This allows us to horizontally scale out the functions to match your incoming load, since each function has no dependency on the other functions which are being executed at any given time. Which also means that if you want to persist data, you can use a service like S3, DynamoDB, or Elasticache. And also, there's no affinity to the underlying infrastructure, which means for the Lambda function, you can't log into the box in which the function is running. So I want to spend a little bit of time talking about the key scenarios and use cases for AWS Lambda. And these are the 3 scenarios which we have seen mostly and widely used today. You are welcome to add to these lists and let us know if you have any other creative applications for using AWS Lambda. But the applications that are used most widely today consist of these 3. The first and foremost one is data processing. As you are uploading data to the cloud, unless you are doing data archival, you want to process that data. And Lambda provides an easy hook for stateless processing of discrete or streaming updates to your data store or message bus. And we have a bunch of event sources which are configured to directly work with Lambda, which allow you to quickly build an application using this setup. Now, whether the data is coming in the form of objects being uploaded to Amazon S3 buckets, now objects could include media files, image files, data files, log files. Any of these sort of files coming in to the system can quickly hook from S3 to Lambda, and you can build a data processing application for objects. Similarly, you can build a streaming data solution using Amazon Kinesis and Lambda, or you could build if your data is coming in the form of table updates to an Amazon DynamoDB table, that can hook to a Lambda function too, or even your logs going to CloudWatch logs, or even your messages coming onto a message bus through Amazon SNS can all hook up to a Lambda function. And therefore, in near real time, you can process all of this data very, very quickly without any management of the system on your behalf. The second big and common use case is application backend development, where you want to execute a server-side backend logic in a cross-platform fashion in a standard 3-tier web application, whether that's a web backend or a mobile backend or an IoT backend. All of these can be very quickly built using a few of the AWS services in association with AWS Lambda. For example, in API Gateway, you can form a web or mobile backend. With AWS IoT, you can very quickly build an IoT backend where these services act as the front end and Lambda acts as the actual logic tier. And if your persistent data store will act as a data tier. So you can quickly build a three-tier application using AWS Lambda. And the last one is control systems, where you can use Lambda to customize responses and create different workflows and to manage the state or data changes within AWS. And this is the integration with different types of tasks which you can build quickly port to Lambda, such as a cron job, especially with the CloudWatch events that we announced recently, or you have different applications where you can run Lambda as a decider logic or a task on simple workflow, or even you have other services such as CloudWatch notifications and SES inbound action rules or config rules, all of these coming into a Lambda function. And you can create these custom control systems very quickly using AWS Lambda. So these were the key use cases I wanted to talk about. But now let's move over to the new functionality that we recently announced. And that was accessing resources in a VPC from a Lambda function. The benefit that you're getting here is you can now access resources such as Amazon Redshift data warehouses, Amazon Elasticache clusters, Amazon relational database service instances, or any service endpoints that are accessible only from within a particular VPC. Now, AWS Lambda runs your function securely within a VPC by default. However, to enable your Lambda function to access resources inside your private VPC, you must provide additional VPC configuration information that includes a VPC subnet and security group IDs. And then Lambda uses this information to set up ENIs that enable your function to connect securely to other resources inside the private VPC. Now we have more information and detailed walkthroughs on this in our documentation, but I will go through setting up your Lambda functions to connect privately to private resources here in this webinar today. But before I get started, I want to do a quick introduction of what a VPC is and how it works. So Amazon Virtual Private Cloud, or Amazon VPC, enables you to launch an AWS resource into a virtual network that you have defined. This virtual network closely resembles a traditional network that you'd operate your own data center on, with the benefit of using scalable infrastructure of AWS. A VPC effectively is a virtual network dedicated to your AWS account, and it is logically isolated from other virtual networks in the AWS cloud. And you can launch your AWS resources, such as Amazon EC2 instances, or RDS instances, or even Elasticache nodes, into this VPC. You can configure your VPC to select its IP address range, and this can be a private IP address range. You can also create a VPC that spans multiple availability zones. And then after creating a VPC, you can add one or more subnets in each availability zone. A subnet is a sub-range of IP addresses in your VPC, and in each subnet must reside entirely within one availability zone, and a subnet cannot span multiple zones. FYI, and availability zones effectively are distinct locations that are engineered to be isolated from failures from other availability zones. So even if one entire data center or one availability zone goes down, the resources in the other availability zone will still work for you, so that your application built across the whole region does not go down. By launching instances in separate availability zones, then you can protect your applications from failures of a single location. And when you create these VPC subnets, AWS assigns a unique ID to each subnet. Now subnets can be of two types. If a subnet's traffic is routed through an internet gateway to the public internet, it is known as a public subnet. An internet gateway effectively is a horizontally scaled, redundant, and highly available VPC component that allows communication between your resources in the VPC and the internet. And it imposes no availability risk or bandwidth constraints to your network traffic. The other type of subnet is that if your subnet doesn't have a route to the internet gateway, such as the one on the left, it is known as a private subnet. And you can route traffic from a private subnet to the internet via a network address translator, or a NAT. And you can use the NAT device to enable resources in the private subnet to connect to the internet. For example, if you want to get some software updates or fetch some data from the internet, or even make API calls to other AWS services. But at the same time, you want to prevent the internet or any resources from the public internet to initiate connections within your private resources. So the NAT device forwards traffic from your resources in the private subnet to the internet or to other AWS services, and then sends the response from these resources back to your private resources. When the traffic goes to the internet, the source IP is replaced with the NAT device's address. And similarly, when the response traffic goes to these resources, the NAT translates this address back to those resources in the private IP subnet range. Now, AWS offers two kinds of NAT devices, a NAT gateway or a NAT instance. We recommend that you use NAT gateways as they provide better availability and bandwidth over NAT instances. A NAT gateway service is also a managed service that does not require any special administration on your part. A NAT instance, on the other hand, can be launched as a DIY from a NAT EC2 AMI, and you may choose to use a NAT instance if you have special requirements on your NAT, or want to customize the NAT itself. So with that introduction to how VPC works, let's talk about how Lambda allows you to access resources in a VPC. The first thing I want to clarify is that Lambda functions always execute securely inside a VPC by default, even if you do not explicitly specify the VPC configuration settings. And this has always been the case. Even before we shipped this feature, ever since we introduced the service in 2014, Lambda functions have always executed securely inside a VPC. However, this VPC is managed by the Lambda system and is not created in your account. So you cannot access resources inside this VPC, and the functions which launch inside this VPC cannot talk to resources inside your account and your account's VPCs. This is where this feature comes in. You can now configure the Lambda function to access resources inside your VPC, inside your private subnets. For example, if you have a Redshift data warehouse or a Elasticache cluster which has the data and you want the Lambda function to have access to that data, you can now configure the Lambda function to talk to these resources in your account in your VPC. And all you need to do is, when you are creating the Lambda function, or once you have created it and you are updating the Lambda function, you add a VPC config parameter to the function configuration. And this config parameter includes a list of VPC subnets and a security group. What happens in the backend is that Lambda creates elastic network interfaces, or ENIs, in your account on your behalf, and then takes these private IPs from the subnet which you provided and associates these IPs with those ENIs. Now effectively the Lambda function has access to the private IP range in your private subnet, and therefore will allow the Lambda function to access resources in your VPC. So let's see this in action today. In today's demo, we will see how to set up a private resource inside a VPC in your account, and then create and configure a Lambda function to access this private resource. The example we'll be using here is reading data off a cache within a private VPC. The workflow will start with the Lambda function. We will invoke this function directly from the AWS Management Console for the purposes of this demo. But this could be any invocation, such as a direct API call made to a CRUD backend, or an indirect API call coming from something like an Amazon API gateway, which you are using as the front end of your application, but the backend, the logic tier, is effectively a Lambda function. In either case, when the Lambda function is invoked, the function will first try to fetch the data from a cache. For this, we will set up a Amazon Elasticache memcached cluster or a node. Elasticache is a web service that makes it easy to deploy, operate, and scale an in-memory cache in the cloud very easily. We will create this node inside a private Amazon VPC, which means that this node will not be accessible to the public internet. It will only be accessible from inside this private VPC. As with any cache-based application, if the Lambda function does not find the requested data from the cache, it will then fetch the data from the main data table, and also it will update the cache. For this main table, we will use Amazon DynamoDB. DynamoDB is a fast and flexible NoSQL database service for all applications that need consistent, low latency at any scale type of responses. It's a fully managed cloud database and supports both document as well as key value store models. Note that here there are two different calls that the Lambda function needs to make here. The first call goes to the Elasticache node, which is inside a private VPC, and the second call goes to a DynamoDB API, which is a public endpoint. For this, we need a couple of additional configuration steps to make this happen. We will create the Lambda function to connect to the private VPC, which holds the Elasticache node. And then we will create a NAT gateway inside that VPC to route outbound traffic from Lambda to the internet, thus enabling Lambda to connect to the DynamoDB endpoint. We could have done this the other way around too, where we create the Lambda function with regular internet access and allow it to talk to DynamoDB, but allow inbound connections into your private VPC that holds the Elasticache node. However, this is not the recommended best practice from a security standpoint. It's always more secure for you to allow controlled outbound traffic from your VPC through a NAT and an internet gateway, rather than opening up your VPC to open inbound traffic, which we don't recommend, which is why we are choosing this route, where we'll configure the NAT gateway inside your VPC, and this gateway will control the outbound traffic connections. So now let's see how easy it is to configure this infrastructure on the AWS console. Note that this is the only demo we have for today, so you are welcome to click along with me and create this setup in your account as a takeaway from this webinar. Now alternatively, given this is a slightly longer demo, and I will quickly skim through some of the background configuration parts, you are welcome to listen in for now, and the slides of this webinar as well as the video recording will be made available to you if you want to replicate this in your setup at your own leisure. So let us quickly set up the ElastiCache node. For this, we go to the ElastiCache console. As you can see here, I'm selecting a single node memcached cluster created on an R3 large type node. You will see that on the advanced settings tab, it asks us for the cache subnet group in order to create this cache inside a VPC. So let's quickly jump over to the cache subnet settings for a bit. A subnet group is a collection of subnets, typically private subnets, that you can use to designate for your clusters running inside a VPC environment. If you create a cluster in an Amazon VPC, you must specify the cache subnet groups that you want this cluster to use. And ElastiCache uses that cache subnet to select the subnet it will run and the IP addresses within that subnet to associate with your cache nodes. So on the cache subnet group settings, you can now create a subnet group and add the subnets from your VPC, from any VPC in your account. If you don't have you can always use the default VPC here, or you can create a new VPC especially for this demo. You will need to add the subnet IDs one at a time for each availability zone. And once you create this subnet group, you can now go back to the ElastiCache node configuration and create your cache node inside this VPC. The node, when created, will now have a private endpoint that will be accessible only inside this VPC. Now let's jump over to the VPC console and look at the VPC that we are using here for this ElastiCache node configuration. The thing to make sure at the left bottom is that you have enough IP addresses available in each subnet, since Lambda will be using these same private IPs from this subnet to scale. You will now need to create an additional subnet in this VPC. As you can see, we have 3 different subnets inside the same VPC in 3 different availability zones. But what we need to do is create one additional subnet and make this as a public subnet, where we will place our NAT instance and route all the traffic to the internet gateway, so that we can connect from this VPC to the DynamoDB public endpoint. So when you click on create subnet, you will get this pop-up screen to configure this subnet. Note that you don't need to worry about which AZ or which availability zone this subnet gets created in, since you will be using this only to connect to the internet. Once you click create, you should be able to see this additional subnet in your VPC configuration. So we have the VPC set up now. Let's move over to creating the NAT and configuring the route table to forward your outbound traffic. On the NAT gateways tab on the left, you can click on create a NAT gateway. To create the NAT gateway, you must specify the public subnet in which the NAT gateway will reside. You must also specify an elastic IP to address to associate with this NAT gateway when you create it. You can also create a new elastic IP or effectively a floating public IP address directly from this console. Here we will select the public subnet that we just created in the VPC that holds this ElastiCache node. After you have created the NAT gateway, you must update the route table associated with your private subnets to point the internet or public traffic to this NAT gateway. A route table consists of a set of rules called routes, which are used to determine where the network flow is directed. Each subnet in your VPC must be associated with a route table, and the table controls routing for that subnet. So here, let's move to the route tables on the tab on the left. Now every VPC has an implicit router and automatically comes with a main route table that you can modify. Alternatively, you can create a custom route table for your VPC. And each subnet must be associated with a route table which controls the routing for that subnet. And if you don't explicitly associate a subnet with the route table, then the subnet is implicitly associated with the main route table. Now, if in the main route table, you don't need to go and explicitly associate all the subnets. Here you need to click on the create new route table and explicitly create a route table for internet access. And you need to set 2 routes in this table. Now, once you have created this, you need to create 2 different routes. The private IP range of your VPC goes to the local host, which will be a default route configuration. You need to add the additional route where all the other traffic at 0.0.0.0 effectively goes to your IGW. Move over to the subnet associations tab. You need to click on edit and then associate the public subnet to this route table. Now, since a subnet can be associated only with one route table at a time, don't associate the private subnets with this route table here. Instead of the new route table which you just created, go back to the default route table and now modify the main route table for this VPC. Here in this default route table, you need to add one additional route for all of your traffic to go to your NAT gateway. With this, you are done with the VPC setup. So what we effectively did here was that your private VPC subnets will be able to talk to resources inside the private VPC itself, the private subnet itself, directly over the private IP space. You don't need any additional configuration for that. Any outbound traffic not in this private IP space will be routed to this NAT gateway through this main route table. The NAT gateway is in the public subnet, and the public subnet is associated with the route table that forwards all outbound traffic to the internet gateway, and therefore the internet gateway will forward the traffic to the internet. So it was a 2-step configuration process which allows the private subnets to still remain in a private IP space, while the public subnet to have your NAT gateway and your IGW to route traffic to the public internet. So now this part of the configuration is done. Let's move over to the Lambda function. Once you log into the console and select AWS Lambda, you can select Get Started Now or create a Lambda function, which will get you to the screen. We have a new approach to creating new functions on the Lambda console, what we like to call blueprints. A blueprint is a set of configurations and sample code to quickly get you started for integrating with a specific trigger or building a specific application. Here I'm going to bypass this and by pressing skip at the bottom of the screen and start building my own function. Let's first walk through the Python code which I'm going to be using for this function demo. Since we need to connect to both memcached and DynamoDB, we will need to import the relevant packages into the Python code. We will initiate the Elasticache settings using the private endpoint that was returned when creating the Elasticache node inside our private VPC. And also we'll initiate the DynamoDB Boto3 client. Now let's look at the main body of the function. As you can see here, the code follows a very simple flow. It extracts the employee ID from the event object and then tries to get this data for the employee ID from the memcache client, which means it is expecting that the employee ID which is passed as part of the event object, the employee ID will be a record in memcached. If memcache returns any data, it will skip this part and directly go and print out this data. And this print statement goes to CloudWatch logs and the return is returned directly to the console. However, if the memcache returns empty, that is, there is a cache miss, then the code tries to fetch the same data from a DynamoDB table. Now it gets the data from this DynamoDB table, with using the ddb client.getItem. And also, after printing that data out, it updates the cache. So it goes back and does a memcache client.set, so that this data will be available the next time somebody the data will be available in the cache next time somebody requests the same data. Note that here I'm assuming that we have already created a table named employee on DynamoDB, where emp ID is the primary key associated with this table, and this table needs to be set up in the same account in which this Lambda function is running. Now for creating the Lambda function with this code, the Lambda gives you three options. The first is to edit the code inline, which gives you the WYSIWYG type editor where you can directly start typing the code. However, because we have a bunch of dependent packages which we need to upload along with this code, such as the memcache clients and the other settings, we can package all of this into a zip file, which I have done here, and upload your code along with all of these dependencies or even binaries directly to the Lambda console. Alternatively, you could have uploaded this zip file to S3 and then provide the S3 object details as the source of your Lambda function, which allow you to integrate your custom deployment tools such directly with AWS Lambda. A few additional configuration settings you would need to make here. The first configuration is to select the execution role of the Lambda function. This is the permission to allow Lambda to take actions on your behalf when interacting with other AWS services. For example, the sample Lambda function needs to read and write data to DynamoDB. It needs to put data to CloudWatch logs. And also, if since you're going to be launching this inside a VPC, it's going to need access to specific EC2 and VPC related permissions on your behalf. The Lambda console provides easy templates for creating these execution roles, or you can even select an existing execution role if you have one. You also need to select the memory of the function that you want to allocate, but let's come back to that. Let's first look at the role creation. So here you need to select the role called Lambda Basic with VPC execution. When you click on that role, it'll bring you to the IAM console with this role pre-populated, and you need to make a couple of quick edits to the role to allow for DynamoDB.star, and this allows you to connect to the DynamoDB as well. As you can see here, there are a few additional settings which the role has. It has a few EC2 network interface related settings or permissions which you need to give your Lambda function to be able to create these ENIs and associate the private IPs on your behalf. Once you have created this function, once you have created this role, if you click on allow, it will automatically redirect you back to the Lambda console, where you can then go and select the VPC settings. Here in the Lambda console, you can, on the drop down, you select the VPC in which you created the Elasticache node, and you select all the private subnets which you used for creating the functions. Now Lambda functions will always launch in the private subnets. Even if you do choose the public subnet, you will not be able to talk directly to the IGW. It will go through the NAT gateway anyway. You also select a security group. The security group allows you to control allows you an additional layer of network control of the inbound and outbound ports which are allowed to communicate through this VPC. Once you create this function and you select next, it will show you a final setting, a list of settings just for you to verify that all the configurations you have set. If everything looks okay, you can select create function and you are done with setting up the Lambda function. So then when you execute the Lambda function from the console, you are allowed to create a test object. And in that test object, I am going to insert one employee ID called 12345. And I'm assuming that at this moment when I have created this, since the Elasticache node is just created, it should be empty, but I'm assuming that this data will be available in the DynamoDB table that we created. So as you can see from the logs here, that the employee ID was not found in memcache, and it is fetching the data from DynamoDB, but it did find the data in DynamoDB, since the print logs on the right say that it is putting it back, setting the data back in memcache right now. Also, if you look at the duration of the function, you can see that this whole step took about 250 milliseconds. But if I execute the exact same function again with the exact same input configuration, the function will, this time, it will execute directly off of the Elasticache. So you see here that the log no longer mentions that this is going back to DynamoDB. It followed the outside loop where outside logic where it quickly fetches the data from Elasticache and prints it out directly on the logs. You can see here that this time the function executed in less than 1 millisecond, because now it is pulling from a cache and it is no longer going to the NoSQL database. So that was our demo for today. Let's talk a little bit about the best practices for enabling the VPC configuration for your Lambda functions. The first one is that you need to ensure that your account has enough ENIs. Since Lambda uses these ENIs for scaling out horizontally, we need to make sure that if the ENIs are available for the Lambda function to build out. We have a quick formula for you to estimate how many ENIs will be required. Now, the ENIs used will be your projected peak concurrent executions normalized to 1.5 GB functions. And also remember that if you rename or delete the ENIs created by Lambda, then Lambda will no longer be able to use these ENIs to connect to your functions, so your functions may start failing. And of course, Lambda will replace them with more ENIs as long as there are more ENIs available in your account. But that's one thing to stay away from. Similarly, you need to make sure that your VPC subnets have enough IP addresses. There will be one IP address used for every ENI created in your account. So if your account, when Lambda finds that it doesn't have enough ENIs or doesn't have enough IP addresses, it will no longer be able to scale out horizontally. So let's say if your account only has 50 ENIs available and you are using 1.5 GB functions, you will be able to scale up to 50 concurrent. But if your incoming traffic increases beyond that, then you will not be able to launch your 51st function, and that will look like a throttle for you. So make sure you have enough ENIs, and also you have enough IPs within the subnet. And Lambda counts the IPs across all the subnets that it is provided. So if you have like 50 each in 3 different subnets, then that counts as a total of 150 IPs. And on that point, we do recommend that you specify at least one subnet in each availability zone. This allows Lambda to run in the high availability mode, where even if one availability zone is lost, Lambda can still execute your functions with zero impact to your workload in the other availability zones. A couple of things to remember when configuring the Lambda functions to connect to your private resources in the VPC. That when you enable the Lambda function you configure the Lambda function to connect to a VPC, the Lambda function will lose internet access. Now, even if you have auto-assign public IP mode enabled on your VPC, it still will not be able to connect to the VPC directly. Now, even if you have an IGW setup in your VPC, the Lambda function will still not be able to talk to to your internet directly. Now, even if your security groups allow all outbound traffic, and you associate that security group with the Lambda function, it will not be able to talk to the internet out of the box. And internet includes other service endpoints. If you feel that all you want to do is connect to DynamoDB, that still counts as an internet call, and you will not be able to make this call directly out of the box. What will work is paired VPCs, and your extended VPN endpoints can be accessed directly through the Lambda function without having any other extra settings to do. For anything which you need to connect to an external endpoint, the only way you will be able to connect to that public endpoints is to create a managed NAT or a NAT instance inside that VPC, put that instance in a public subnet, and then configure your route tables to connect those private subnets to the managed NAT. That's the only way in which you will be able to get public internet access to your functions. And the thing to note here is, which also means that if you explicitly do not need to connect to private resources, if what you are going to do is create a Lambda function which connects to a private subnet, and then in that private subnet you just allow outbound traffic to connect to public endpoints, at that point you don't need to specify the VPC settings. Now, as I said, Lambda runs inside a VPC, so the Lambda function is secure. Enabling this VPC configuration is not adding to your security, it's only allowing you to connect to private resources. So if you don't need to connect to private resources, you can run Lambda functions without the VPC mode. This setting is to be done only if you have to talk to both private and public endpoints in the same Lambda function. Now, as we saw, you want to connect both to a private Elasticache node as well as a public DynamoDB table in the same function. That's only when you need to create this Lambda functions inside this VPC. So with that said, that's we're coming to the end of the presentation here, but I do want to take away with give you 3 next steps. The first is to create your first Lambda function if you haven't already. With Lambda, there are no new languages, tools, or frameworks to learn. As we saw, you can import third-party libraries or even native libraries. And remember, every month, the first 1 million invokes are free. So we do encourage you to try out Lambda today. The next thing to do is to connect your Lambda function to resources inside an Amazon Virtual Private Cloud by adding the VPC config parameter, either at the time of creating the function or by updating the function or updating the function configuration of an existing function. And of course, we do encourage you to try out creating the network address translation or a NAT instance inside the VPC to enable your Lambda function to connect to both resources inside the VPC as well as endpoints on the public internet. So thank you very much for listening in. We will, Ajay has been addressing the questions on the Q&A panel so far. We will also be taking up questions publicly since we have about 10 minutes left here. But if any of the questions were not addressed, we do encourage you to post your questions to the Lambda forums, and we'd be more than happy to address them offline. We also have a lot of information around Lambda on our documentation, on our compute blog, as well as on the Lambda detail pages. So we do recommend that you do have a look at those. A quick call out for folks who are in and around the Midwest or are open to traveling to Chicago. We have the Chicago Summit coming up in mid-April, which is a free cloud conference designed to educate you and inform new customers about the AWS platform, best practices, and new cloud services. We have the details here on this slide. We do recommend that you if possible, do visit this conference. The Lambda team will be there, and we'll be happy to address your questions in person at that time. With that, I'd like to take a quick 2-minute break, and then when we return, we can walk through some of the more frequently asked questions in this public setup. Okay, thank you so much. Be back in a couple of minutes. Back to you, Bowen.
Thank you, Bill. Now on your screen, everyone, you can see 3 poll questions to the left of your screen. Please fill out those poll questions. Your feedback helps improve our webinar programming. I know Ajay has been answering lots of questions. At this point, we have about 10 minutes. So if you have any questions on Lambda and especially on today's presentation on VPC support, please submit questions at this point. We apologize in advance that we may not be able to get to everyone's question, but we'll let William take a 1-minute break, and once he's ready, we're going to answer a few questions. Thank you.
Okay, thanks for your patience. I'll I'll go through a couple of commonly asked questions here. I have a question from Zach. Is an ENI assigned per Lambda invocation? And a similar question from Mark. Will Lambda take a private IP per function? So as I mentioned, the way Lambda will work is that on the back end, we try to optimize for the fewest number of ENIs and private IPs to be used. So we do try to club everything as close together as possible, which means that we normalize the number of IPs that you will use to a 1.5 GB function times the max concurrency which you are using. So if you're using a 1.5 GB function, then you can assume it's almost a 1-to-1. But if you are using, let's say, for example, a 0.5 GB function, then one ENI and one private IP will be used every three functions or three concurrent functions, which also means that if you invoke the same function serially, one after the other after the next, then that still will take only one IP. Only if you execute three functions concurrently, then Lambda will scale out and all three will use individual IPs. I have a related question by Ryan. Is the number of concurrent Lambda instance limited to the number of available IP addresses in a VPC subnet? So yes, that's the way it works, except that it's not only a VPC subnet, but all the subnets that you provide. So we'll try to use an IP address available in whichever subnet is available. So if one subnet has only 50, but the other subnet has 1,000, then if we run out of IP space in one subnet, we will automatically fall back to the other subnet, and we will try to distribute the load between those two subnets. And we will be able to scale up to using up to 1,050 concurrent Lambda functions, normalized again to 1.5 GB, after which we will no longer be able to scale. So what will happen is that on your you will get an error that says VPC you had a shortage of private IP, so you'll get an error message which says you ran out of IP spaces, and that will be treated as a throttle, and Lambda will automatically try to retry that with a little bit of back off, so that your functions will get effectively queued up and you can process them over time. I have a question from Zio Yang. If we use Lambda as my 3-tiered backend app tier, would the latency become an issue? So I'd like to call out the difference here of so Lambda works in a slightly different way, where the first time you call the Lambda function, it has to do a bunch of configuration on your behalf. Now things like behind the scenes, if you're using, we use Linux containers to run your Lambda functions. So we need to do things like spinning up the Linux container, booting the runtime application, and for example, if you're running Java, then we boot up JVM. We download your code from what you have uploaded onto the system, and then we bind your code to that system. As an extra for things which you are running inside a private VPC, Lambda needs to do a couple of additional steps. That is to create an ENI in your account, to select a private IP address from your subnet, and then associate that private IP address to that ENI. So all of these steps are needed for the very first invocation. So you might see some additional latency, what we call the cold start latency, when you are building the backend app tier. However, when you invoke the function the second time, now all of these resources now already exist in your account, have been set up for you. The second invoke, as you saw in the function, the first invoke takes a little bit longer, but the second invoke will take much lower time. And of course, the latency effect that we got was because of a cache, but you will see very similar behavior where the first invoke will take seconds, while the second invoke will be in milliseconds of latency. So hopefully at scale, you will start seeing less and less of this impact, and especially if you have a steady state workload, then except for the first time when you are starting up, this impact will go away. I have a question from Kamlesh. Can the database be hosted in a corporate network, or does it have to be an AWS hosted database or an RDS connection for Lambda to access it. So since the Lambda can connect to any VPCs, if you have a VPN which you have peered to your VPC, you will be able to access the whole IP range of your VPN from that private VPC. So for that, you don't even need to have any special setup. If your VPN is effectively peered to your VPC, then you can directly access any private endpoints inside your VPN. What you would need to do though is that if you don't have individual IP endpoints to hit, since your traffic will be going through a border gateway which you have connected on the AWS side of your VPC. If you're, instead of an IP range, if you're using a internal.mycompany.com type of domain which you are using to connect to, then the Lambda VPC takes a couple of seconds to resolve that the domain into a actual IP address. So the first couple of calls may fail, but those will automatically get throttled and retried. And effectively, once the connection is established, once the Lambda knows what your endpoint is actually pointing to, it will be able to communicate directly to that endpoint. We have a couple of questions around from Charles and now also from a couple of other folks on how connection pooling would work with RDS. So today, the way you could handle this is the way I did it in my source code, if you initiate your RDS connection outside the handler function. So if you remember, I created the Elasticache cluster and the database connection outside the handler function. I created it directly inside the main body of the source code. So those connections will then be commonly shared across all the invokes which you are doing. If you create the connection with RDS or with Elasticache inside your function, then for every invoke it will try to recreate the same function. At the end of the invoke, it will tear that function down, tear the connection down. However, if you create the function outside the handler, then the connection needs to be created only once, and then it will be shared across all the invocations that happen on the same container in a serial manner, so that the connection to the RDS doesn't, you don't need to hit the RDS connection each time. All you need to do is just transfer data on an open connection which you already have created. And then eventually, when that container, when your workload goes away and that container terminates, over time these connections will time out, and therefore you will no longer have, the connections to RDS will be terminated. Okay, we are at the top of the hour, and I'd like to respect everybody's time here. So apologies if I wasn't able to address all of the questions. No, please do direct your questions to the Lambda forums, and we'd be happy to take those those questions there. Thank you very much, and have a great day. Bye bye.